next speaker is James Oreluk. James Oreluk is a postdoctoral researcher at Sandia National Laboratories in Livermore, California. He earned his Ph.D. in mechanical engineering from UC Berkeley with research on developing optimization methods for validating physics-based models. His current research focuses on advancing uncertainty quantification and machine learning methods to efficiently solve complex problems, with recent work on utilizing low-dimensional representation for optimal decision-making. The title of his talk is A Bayesian Optimal Experimental Design for High-Dimensional Physics-Based Models. Please welcome Jim.
So, I'm going to start. Let's let the clicker work. I'll just turn it back on. All right. So thank you for the introduction. Today I'll explain what Bayesian optimal experimental designs are and how we can use them to kind of learn something about our physics-based models. And this is work that I've done with my colleagues, Lenny Sheps and Habib Najim at Sandia. And so this slide's a little bit silly, but when we go out and run a test or collect experimental data, we're really trying to improve our knowledge or understanding of a problem. And so myself, I'm a computational scientist. And so when I think about getting experimental data, I'm trying to learn something about my model. So maybe on the left here, we're trying to learn some unknown parameter in our model. So in blue, we have some prior distribution of the uncertainty of this parameter theta. And after we observe some data, we can condition on that data and get a posterior distribution that's shown in red as a new update. Alternatively, we can kind of think about problems where we have a field and there's two sources that are placed in the field, but a priori, we don't know where they are. And we'd like to take measurements in the field to kind of adaptively learn where these sources are. And we'd like to make the minimum number of measurements sequentially to kind of refine our estimate of where these sources are located. And then on the right-hand side, you can kind of see that we're trying to improve the predictivity of a quantity of interest or QOI. So let's say I have a model, it's making a prediction of how far a missile is going to go, or perhaps the temperature of the wall of a reactor. In blue, we have our prior predictive distribution. So this is without any data, and it's far too large to be acceptable. So we want to gather experimental data to update our predictions to kind of reduce the uncertainty so we can make a better prediction. And so in all these cases, what we're really doing is decision-making. We're deciding where to gather data to help us learn about our problem. And so down here, what experiment or test should we conduct that's going to be most beneficial in terms of learning our goal, whatever goal that may be. And so, today I'm going to talk mainly just on the left-hand side, we're going to be learning how to find designs that help us learn particular parameters in our model. And so if we take a step back, we have this design loop where we have some prior distribution on our parameters that go into this loop. We want to find some optimal design. We'll talk about how we do that in a sec. And then what comes out is an optimal design denoted D star, D being the design condition, star optimal. And then we can go ahead and run an experiment at D star and collect some data Y. And then we can update our prior probabilities, conditioned on that data, doing things like Bayesian inference. And so if we just zoom in into what each of these blocks shows, really the optimal experimental design problem is just an optimization problem. We're trying to maximize some function, capital U of D. It's an expected utility. We'll talk about that. Then we can conduct an experiment. We're going to be looking at mass spec data. And then, of course, updating probabilities. Since we're taking a probabilistic view on uncertainty, we're going to be using Bayes' theorem. Okay, so the experiment that we're looking at and the problem I've been studying for our project really deals with the low temperature oxidation of propane. Why? Well, when propane actually breaks down to a ton of intermediate species, those intermediate species react with one another, and their reaction rates are actually very poorly known, and they can have a huge influence in our simulations. And so we'd like to understand those uncertainties in those reaction rates much better. And so the experiment we're looking at is a high pressure photolysis reactor. I'm not an experimentalist. A CAD drawing is shown on the top right, but it's a flow reactor. So premixed fuel flows into the reactor, it reacts, it flows out into a photoionization mass spectrometer. And on the bottom right, we get a snapshot of some of the data that we collect. This data was collected at a fixed energy and time. And so we can see this kind of all these peaks that appear in time of flight from this mass spec. And each of those peaks is showing the presence of an unknown maybe species, in the reacting gas mixture or some daughter ions. And of course, we can sweep across energy and time, so we can collect a tensor of data that's at extremely high resolution. Okay, so why don't we just go do that? Well, of course, experimentation and test is both costly and laborious to conduct, right? We can't just go out and run tens of thousands of experiments. And for this particular experiment, the instrumentation and where it's conducted is at the Advanced Light Source at UC Berkeley National Lab. So we have a fixed schedule of when we can actually operate this experiment. So come back in 3 months and you can run a couple times. So we would really like to use a computational model of this experiment to help inform us of where we should be running our experiments. So how do we develop a computational model of an experiment? Well, first we need to decide on a data model. So we'll say that the data that we collect from the experiment is Y. And so I don't know if I have, yeah, I do. Okay, so Y is our data, and we're going to say it's generated by some true physical process C. So this is the actual reactor experiment, but that measurement has been corrupted by some additive noise epsilon. So this is the instrumentation or the data noise. So we don't have access to the true physical model, but we do have a computational model that tries to mimic its behavior. It takes in parameters theta. These are these uncertain reaction rates that we're hoping to learn something about. Now, this computational model is an approximation of reality. There are deficiencies in this model. For example, reactions occur on the wall. Well, our model doesn't consider that. So we want to account for those discrepancies in our computational model by adding this term delta to account for model deficiencies or model errors. So we're modeling the model error as a Gaussian process model parameterized by some mean and covariance function. We assume we know the kernel for this covariance as well as the length scale. I think in a couple talks, there'll be a talk on how to handle uncertainty in GPs a little bit more concretely. Most of our uncertainty is in the parameters themselves, theta. Okay, so what do we get out? Well, if we calibrate this experiment or this model to some data, so on the bottom right, we can see a plot of a peak for propane. So this is C3H8. And in the blue curve is our computational model by itself. Does a pretty good job. The black points are the data, but we can see at the tails, our model assumes every peak's a Gaussian, but the data itself is not a Gaussian. And so including model error helps us, account for these non-idealities that we actually see in the real data. Okay, so now we have a computational model, so let's kind of learn about Bayesian optimal experimental design. So Bayesian optimal experimental design aims to find conditions that maximizes what's known as an expected utility. So this is this maximization problem that we haven't seen before. And so why are we looking at an expected utility? Well, we're looking at expected utility because when you go out and run an experiment in the real world, you don't know what data you're going to see, so that's the Y. And we also don't know what parameter in our model actually generated that data. So that's why we have theta. So we have this joint density over the parameters theta and the data Y. And then we have this function U, this utility function in front. So of course you can just write this joint density as just a posterior distribution times Bayesian evidence or the marginal likelihood. But so what do you select as our utility function, right? So that's the big question. So the utility function really needs to model the desirability or the preference of the experimenter for given experiments. So if we're interested in estimating an unknown parameter value, well, if I run an experiment and I see really no change in the density, then that I would not have much preference there. But if I see a large change, okay, that's a high preference. So how do we quantify that? Well, we're going to be looking at the Kullback-Leibler divergence, which we heard about earlier. And so just pictorially down below, what does that look like? Looking at changes in distributions, right? And so associated here, small change from our prior shown in black and blue, the posterior. We see a small change that's associated with small Kullback-Leibler divergence. And conversely, on the right, there's this large change or large. So this is exactly what we want in a utility function. Large shifts in our parameters are quantified by a large value. So let's use this as our utility function. I think in the interest of time, I'm going to skip over this slide, but utility function, we can aim at different goals. So if we care about predictivity, we'll just choose a different utility function to quantify that. So if we plug this into the formula we've seen before, I'm not going to mess around with the math too much. I know there's a lot of math here. So we end up with this kind of intractable double integration on the bottom. Can't solve it. So how do we actually go about doing that? Well, we need to make a numerical approximation. Specifically, we'll do Monte Carlo integration. And so we're left with this top equation here, where we're looking at the difference between the log likelihood and the log marginal likelihood. And so we can actually evaluate this, but this second term, this log marginal likelihood, or the Bayesian evidence, is a nasty thing to actually solve for. So how do you do that? Well, you can do importance sampling. You can do variational methods. In here, and what's classically done, is yet another Monte Carlo estimate. And so you get this kind of classical result, which is called the nested Monte Carlo estimate of our expected utility. And so this has a estimate within another Monte Carlo estimate. And so this equation in the middle of the slide is something we can actually solve for. So we can say what the value of a particular experiment is at learning parameters. So it's something that we can compute. However, it's not good enough just to compute it. We want to maximize it, right? We don't care about just computing how valuable an experiment is. We want to know what the most valuable experiment is. So we need to optimize this function. Of course, valuing this is kind of costly. It's an expensive function to compute, as well as we don't have the derivatives for free. So optimization through gradient-based methods is kind of off the table, unless you want to find the different things, but that's another thing. So how do you, optimize a function where you don't have the gradients, it's costly to conduct? Well, first thing I think of is Bayesian optimization. This is a one-slide summary of it. In case if some people are not familiar with it, I'm probably not going to give it a good explanation, but I'll give it a shot. So we want to optimize some objective function. We don't actually know what it looks like throughout the entire design space. So we're going to build a surrogate model that tries to approximate it through the design space. Specifically, we're going to assume it's a Gaussian process. And so we don't have gradients to decide where to take our next optimization iteration. To kind of guide the procedure, we're going to follow an acquisition function to select new samples. And specifically, we're going to be looking at taking our next optimization iteration to maximize this acquisition function alpha. And so on the right is just a toy example trying to illustrate this. And so in black, we have some this is the true but unknown utility function. So we don't have access to this, but we've sampled it, I think, 4 times here. So we have 4 stars on the plot. We're going to fit it with a Gaussian process that's shown as blue. So we have some mean of the Gaussian process, as well as the 2 standard deviations of the shaded region. And so where do we take our next point? Well, we'll take our next point by calculating this the acquisition function, which is just a linear combination of the mean plus some scaling on the standard deviation. And so if you can see the plot down below, and we'll take a point at the next point at 0.5. And so where does the acquisition function become large? Well, it becomes large if the mean value is large. So that means we know that the value of our function is quite high there because the mean of our Gaussian process is high. Or it's going to be large if the standard deviation is high. And that's regions of the design space where we have a lot of uncertainty about what the function looks like there. And so you get this trade-off of exploitation versus exploration when you're doing the optimization procedure. Okay, so job's done, right? Well, no, because when we deal with high fidelity physics-based simulations, they're very costly to evaluate. And like I kind of maybe alluded to, calculating this expected utility is on the order of n times n forward solve. So if you have any decent physics-based simulation, this is just intractable. And so one thing you do is, well, we could build a surrogate model, some cheap analytical representation of our output to kind of address the costly runtime. We just have too many outputs to actually do that in our problem. We have something like 100,000 to 10 million non-zero elements from this tensor output. So we can't build a surrogate for each element. And so we really need to strive for low dimensional representation of the output. So we have this output, can we compress the information in some meaningful fashion and then build surrogates in this low D space? There's various ways you can do data dimension reduction. You can think of diffusion maps or autoencoders, and that's in fact what we started with, but good old SVD seem to work quite well. I think I'm okay on time. So SVD, just a summary of how you do this. So you can generate some samples from your prior and evaluate your your costly model. And you build up a matrix where Y is n by j, where n is the number of samples and j are the number of outputs. So you have this big matrix. And then you're trying to, you can perform SVD to break it up into 3 very special matrices. And you can retain the top k singular values of S, and what you get is the best low rank approximation of k by rewriting in following sense. And so why is it even worthwhile to do this exercise? Well, if we look at VK, It's a projection that allows us to project our high D space down to a low D space. So it's a linear combination of all these outputs that can be summarized into like a fewer number of elements. And what that's good for us, because now we don't need to build surrogates for all J elements. We can do it for a very small number of K elements. And so on the right-hand side, it's just showing for one of the examples, we can summarize about 94% of the variance just with like 10 components. So we don't need 100,000 surrogates, we only need 10, and we can lift it back up to the original space if necessary. Okay, the last challenge I'm going to talk about before showing results is everything I've discussed so far dealt with looking at changes from prior to posterior, right? We're quantifying how valuable an experiment is, changing these densities, but we really don't care about changing the entire density because in our particular case, we have something like 1,100 different uncertain reaction parameters going into our model. We only care about maybe some, like we want to find designs that improve some of those parameters. So on the right-hand side, this is our target set of reactions. There's like 25 of them. So you can imagine we're trying to find experimental designs that target these parameters. So we want to learn them, not the whole density being shifted, because perhaps we don't care about the first parameter changing. And so to do this, it's just yet another technique in marginalization. So we can say, well, we have parameters we care about theta and parameters we don't care about eta, which we're calling nuisance parameters, and we can integrate out their effects in the likelihood. So this introduces yet another loop in this very expensive procedure in our expected likelihood, or sorry, the expected utility. So you don't have to just follow Monte Carlo estimation to kind of do this integration. You can do important sampling, and there was a paper by Marzouk that kind of talks about that. But in our work today, what we're showing is just all Monte Carlo integration. Let's say putting everything together. The targeted workflow that we're looking at is, we want to generate a random sample in the design space. So we just randomly sample, uniformly, Latin hypercube type sampling, and then we compute U of D for all these samples. What's nice is this first two elements you can perform in parallel, and then you can go run the Bayesian optimization procedure, which is a serial procedure, to find the best optimal design. Now, of course, you're done if you have a very cheap model, but in expensive models or more physics-based models, when you're computing U of D, the first thing you should do is a sensitivity analysis, because you don't expect all 1,100 parameters to be sensitive at a given design. Only a subset of those parameters are actually influential. And then you check, were the sensitive parameters, even the ones I cared about? If the parameters that are sensitive at a given design aren't the ones we care about, then gathering data at that design is going to provide no information of the parameters we care about, so we can assign zero utility to it. But if they are in our target set, then we can sample them and construct these low D surrogates as we had just discussed. Okay. And so results. So we've applied this for the high pressure photolysis reactor experiment. Like I said, we have 1151 uncertain parameters here. The design space that we're looking over, that we're trying to optimize over, is both, it's 4-dimensional, so it's relatively low D. We're trying to optimize the temperature and the pressure of the reactor. So what temperature and pressure should we run the experiment at, as well as the number density of chlorine radicals and O2 in the reactor. And of course, we're looking for propane, so we're actually having propane be fixed, the number density here. So it's not one of the kind of knobs to tune to run the experiment at. We're also assuming that the model error is independent of design, and we're making kind of a severe assumption here. It's mainly for tractability, and we're currently loosening this assumption that we have some sort of structure in the covariance of this model error. Okay, and so results. And so target 2 is just the target set of reactions that I had shown earlier, those 25 some reactions. The plot on the left, the black points are showing random samples in the design space. So if I were to just randomly run an experiment, how valuable would that be in terms of learning those 25 reactions I care about? Well, you could see, well, a majority of the 250 random samples provide little to no information. So this tells you if you go out and run an experiment in the real world, if you're trying to target these 25 reactions or learn about them, you're going to get nothing. Very few of those 250 actually provided some information. Okay, so let's turn on Bayesian optimization. So that's shown in the blue here, and you can see that we quickly improve on the random sampling result, which is not to be unexpected. Of course, random sampling versus optimization. We were stressing for exploration, so we don't actually see any improvement beyond that first point. But the point is that we're able to find designs that actually improve the estimate of the parameters we care about, right? Randomly sampling is not going to get you there. On the right-hand side, I'm showing, this is a parallel coordinate plot because it's hard to visualize 4D spaces. And so we have temperature, pressure, these design conditions, and the expected information gain, which is our expected utility view. Highlighted in red is high values, and you can see it etches out kind of a region in this space. So it gives us some idea of temperature ranges as well as pressures that we can run the experiment at that provides actually valuable information. We could fix 2 of the coordinates and then do a contour plot to visualize the design space. So these contours are associated with high information gain or high expected utility. And you can see the optimal is here in the corner. And so this is really good to give to an experimenter or tester because it allows them to maybe select something that's maybe suboptimal if there are safety concerns at this optimal design. So maybe they'll want to follow on the contours, or maybe perhaps resources are limited. So they want to reduce the amount of chlorine radicals used in the experiment. Get something that's valuable, but maybe not unsafe. Okay, and so what does the posterior distribution look like after we've taken a measurement at D-star? And so we've just run the experiment and we're currently analyzing the results. So I don't have those to present to you today, but what I can show is, well, we can use our computational model to generate plausible data sets at D-star. And then each of those data sets are equally plausible, get a posterior and aggregate them together with logarithmic pooling, which is shown here. So it's really just a weighted average of all these plausible data sets and combining it to give us one posterior distribution to show you. Okay, so on the left-hand side, I'm showing, again, a slice because the data is in a 3D space of energy, time, and the time of flight. And so I'm just looking at a slice here and showing you what the plausible data sets look like. And so if we kind of go around, you could see as we sample plausible data sets, we see the presence of new species and the magnitudes of the peaks change quite a bit. So there's a lot of interesting things happening at this design condition. On the right-hand side, we see a posterior density. And of course, first person would say well, there's not 25 parameters. Well, at this condition, not all 25 parameters we cared about were sensitive. So only 5 of them were. So that's what I'm showing you here. And so what you can see is, well, initially we had prior distributions that were standard normal. So the ranges should have been roughly -2 to +2. And so you can see the density shifted quite a bit, and there's been significant learning. Also, we can see that there's correlation between 1044 and 1049. So these are 2 reactions. I'm just showing those reactions on the left-hand side. Don't need to have a chemistry degree here, but propylene oxide is a shared product species between these 2 reactions. So if we see data on propylene oxide, it makes sense that these 2 reactions should also be kind of correlated because they're both trying to produce the same thing, right? So there's correlation between those 2 species. And so this is really exciting for us because it allows us, this Bayesian optimal experimental design to kind of find experiments that target very specific parameters that we care about in very complex models. And so with that, just wrapping up in conclusion, so we show that it's feasible to use Bayesian optimal experimental design for these very difficult problems. Bayesian optimization really helped us optimize these noisy objective functions, and this would not be possible computationally without these low-dimensional representations of these complex physics-based models. And so the future work is really to just demonstrate that with real data, we do see an improvement in the posterior distribution versus random sampling. And then also all the work that we had shown, the prior density was informed by the literature. We do have data collected, and so our initial prior should use that data originally. And with that, I'd just like to give thanks to some colleagues as well as the DOE and the Basic Energy Science for the funding for this work. And I'll take any questions at there's time.
3 minutes for questions.
Okay.
You're talking about the random sampling. Are you talking about like a space-going design or just purely random sampling?
No, yeah, space-going design. So I did a Latin hypercube, 250 samples, and then I kind of broke it off onto various nodes to do it in parallel to evaluate that expected utility. And so it's like if I randomly sample that 4D space, how much value would we see in that experiment? It's not going to be much. So if an experimenter goes out in the real world and just randomly changes the temperature and pressure and concentrations, we wouldn't see much improvement in these parameters we care about. Yeah.
Did you explore other utility functions, maybe a trade-off between what you have, which is pretty ideal, versus one that's less computational?
Yeah, so this is called that Wheeler divergence. So there's an information theoretic point of view, and that's the one that's kind of preferred. But yeah, it's definitely interesting to use other utility functions because maybe we don't really want to see a shift in the mean, but only care about changes in the standard deviation. And then, yeah, we could concoct a new utility function to kind of prefer those experiments instead. Yeah, that's a good.
On the optimization, you compare it against something like conjugate gradient methods. So what about something like simulated annealing?
Yeah, I mean, that's also great for optimizing things when you don't have derivatives. So we have only used the Bayesian optimization procedure for optimizing, but yeah, simulating annealing or any derivative-free optimization would be, great for these sort of problems.
You said you emphasized exploration in your design. Did you look at changing? I think you had like a data parameter.
Yeah.
Have you looked at?
No, for this particular work, we ran the one results. And so we had data, I think at 3 here. And so for different targets, sometimes we did see a little bit of improvement beyond that initial one, but it's definitely a knob to tune to see if we can kind of emphasize, refining this, these design conditions. Yeah. Thanks.
Maybe one more question. Anybody has one?
Yeah, so what does it mean? You had a contour of your design. I think at one point the optimal was on the boundary.
Yeah.
The bound of that parameter. And does that mean it's like the trickier experiment maybe to do? And
Yeah, so the experimentalist said, I only am comfortable with going with this number density of chlorine, and so that's the bound. And often in these physics-based models, we kind of see that the optimal tends to lie on one of the boundaries. Yeah, we can definitely push it up, and most likely it'll fall somewhere else. But for experimental reasons, we have this kind of constraint there. Yeah.